A bus makes three displacements in the following order. 1. 58 miles, 38 degrees north of east. 2. 69 miles, 46 degrees north of west. And 3. 75 miles southeast. A. Draw a clear diagram showing all three displacement vectors with respect to horizontal points, north, east, south, and west. So if we show vector 1 first, so first thing to do is on our graph to show north, east, west, and south. So that'll help out when drawing our three vectors. So if we draw the first one, it's 58 miles, 30 degrees north of east. So we would have a vector 1 like this. Then vector 2 is 69 miles, 46 degrees north of west. So if we draw small axes here, we're doing a 46 degrees north of west. So west direction is that way. So if we draw 46 degrees north of west, we would have a vector of this magnitude here. And now our third vector is 75 miles southeast. When they say southeast, it means at a 45-degree angle completely in between south and east. So it's at an angle of 45 degrees. So we do this at an angle of 45 degrees for 75 miles, looking like this. And then our resultant is the origin of 1 and the endpoint of 3. So our resultant is along the lines of this. Now, my picture may be off a bit. The resultant may be over here somewhere, but this gives you a general idea of what direction the resultant vector is pointing. So we know it's somewhere in the northeast direction. So we know that both its x component and y component are both positive. So for part B, we have to find the x and y components of displacement d1. So if we draw out our axes again, and our first vector, 1, we have it of the form of this, and this is at an angle of 38 degrees. We now want to find d1 of x and d1 of y. In order to do that, we have to find the components. In order to do that, we have to apply SOHCAHTOA. So in order to solve for d1 of x, we're going to use cosine of theta is equal to the adjacent, which is d1 of x over the magnitude d. So we'll interpret 1 now as d. And in order to solve for d1 of x alone, we multiply both sides by d, giving us d1 of x is equal to d cosine of theta. If we now plug in our given values, d1 of x is equal to 58 miles times the cosine of 38 degrees. If we now evaluate this, we would find that d1 of x is equal to 46 meters. So it's 46 miles, miles. Make sure you keep the correct units when doing these. Then for d1 of y, by also applying SOHCAHTOA, we find that the sine of theta is equal to the opposite, which is d1y, over the hypotenuse, which is d. If we now solve for d1y by itself, we multiply both sides by d, giving us d1 of y is equal to d sine theta. If we now plug in our given values, d1 of y is equal to 58 miles times the sine of 38 degrees. If we now calculate this out, we would find that the magnitude of our y component is 36 miles. Part C says find the x, y components of displacement d2. So once again, if we draw our axes here, and now we're going to draw in our second vector, which is 69 miles, 46 degrees north of west. So it's of the form here. This is our d2. Now this here is 46 degrees. We want d2x and we want d2y. In order To solve for these values, we again have to apply SOHCAHTOA. So for d2x, we're going to have cosine of theta is equal to our hypotenuse, the adjacent first, which is d2x over hypotenuse d. If we get d2x alone, d2x is equal to d cosine of theta. Plug in our given values, d2x is equal to, value for d now is 69 miles, and it's the cosine of 46 degrees. If we now calculate this out, we would get a magnitude of 47 miles, but take notice that we're pointing in the negative x direction, so we assign it a negative value. So d2's x component has a magnitude of 47, but it has to be negative because it's pointing in the negative x direction. Now we have to calculate d2y. So applying SOHCAHTOA again, we see that sine of theta is equal to the opposite, which is d2y, over the magnitude of the hypotenuse, which is d. If we now solve for d2y on its own, d2y is equal to d sine of theta. If we now plug in our given values, d2y is equal to 69 miles times the sine of 46 degrees, which will give us a magnitude of 50 miles, and since our y component is pointing in the positive y direction, it is also positive, so we have 50 miles for d2y. Part D says, find the x and y components of displacement d3. So again, if we draw our axes and our third vector, which is 75 miles southeast, which is a 45-degree angle with respect to either of these sides. We then want to find d3x and d3y from this. So again, we're going to apply SOHCAHTOA. So I'm going to use the angle here for these two components shown here. So we're not going to use this angle, we're going to use this angle here. So for this, to solve for d3 of x, we're going to use the cosine of theta is equal to d3 of x over d, the hypotenuse. If we now solve for d3x on its own, we get d3x is equal to d cosine of theta. If we plug in our given values, we find d3x is equal to 75 miles times the cosine of 45 degrees. Because remember, it says southeast, so southeast is exactly in between north, south and east, so it makes a 45-degree angle with respect to both the east axis and the south axis. So this is what the equation we have for d3 of x. If we now evaluate this, we get a magnitude of 53 miles, and again, check the direction. So you can see that d3 of x is pointing in the positive x direction, so it's assigned a positive value. Now we have to solve for d3y. Using SOHCAHTOA, we see sine of theta is equal to the opposite, which is d3y, over the hypotenuse, which is d. If we now solve for d3y on its own, we multiply both sides by d, giving us d3y is equal to d sine theta. If we now plug in our given values, we have d3y is equal to 75 miles times the sine of 45 degrees. This will give us a magnitude of 53 miles, but you have to take notice that our d3y is pointing in the negative y direction, so we give it a negative 53 for our component d3y. Part E wants you to find the magnitude of the resultant vector. So we want to be able to find, so if we draw axes again, we want to be able to find that resultant vector that we have shown in the beginning, this r value. So in order to do that, we need to show the sum of the dx's and the sum of the dy's. So we're going to go over here and add up our columns. So 46 miles plus negative 47 miles plus 53 miles gives us a total of 52 miles, and then 36 miles plus 50 miles minus 53 miles gives us a magnitude of 33 miles. So if we now apply the Pythagorean theorem to this, we would see that r squared is equal to sum of dy squared plus sum of the x's squared. Now if we want to just solve for r on its own, we take the square root of both sides, giving us r is equal to square root of what we previously had. So there we have it. This is what r is. Now the problem is in calculating this out. So we have solved for the sum of the x components and the sum of the y components. So we simply plug that into the equations here. We're going to get 33 miles squared plus 52 miles squared. Now if we calculate this out, 33 squared is 1,089 square miles, and 52 squared gives us 2,704 square miles. If we add those two together, we get a total for r to be the square root of 3,793 square miles. And if we now take the square root of that, we would find that the magnitude of our r is roughly 62 miles. Now when you actually take the square root of this, square root of 3,793, you'll get a value of 61.587 and so on. But we're using significant figures when we're doing these, so we have two significant figures given in our givens, so we also have to remain with two significant figures. So we have to round up off the basis here. This is 5 or greater, so we round up to a value of 62. So that's why we have a value of 62 miles and not 61.587. So just keep that in mind when you're doing these problems. Check on your significant figures when it matters. Part F says find the direction of the resultant vector. So we have shown that our resultant vector is along these lines here. It has a magnitude of 62 miles, as we have shown before, and we now want to calculate what direction it's pointing with respect to the x-axis. So if we again show the components, so the sum of the dx's, the sum of the dy's, corresponding to our resultant vector r, we now want to find this angle here. Now you could use sine or cos, but you would have to go off of the answer for your magnitude of the resultant vector, which is something you had solved for off the basis of knowing the sum of the dx's and the sum of the dy's. So if you did make a mistake in solving for the sum of the r's, you don't want to carry that mistake out here, where if you made a mistake in the dy's, it would just carry through and you wouldn't lose as many points as if you solved for the dy, then did r wrong, and then took the r wrong and put it into here. If you did all the dy's correctly and only made a mistake in the r's, and if you use the dy's and dx's again, you wouldn't use something that you did wrong in the final here. So I'm going to use tan of theta, which is the opposite, which is the sum of the dy's over sum of the dx's, which is our adjacent. Now, when we do this, we're going to solve for theta. So, in order to solve for theta, we have to take the tan inverse of both sides. So that gives us tan inverse of the sum of the dy's over sum of the dx's. If we now plug in the values that we have over here, we have theta is equal to tan inverse. Sum of the dy's is 33 miles, and sum of the x components is 52 miles. And if we now calculate this out, we would find that our angle with respect to the x-axis is 32 degrees. So we have shown that the magnitude of our resultant is 62 miles, as we have shown here, and we have just shown that our resultant makes an angle of 32 degrees with respect to the x-axis. So we're pointing in the northeast direction at an angle of 32 degrees.